So when you're writing Go code, you're constantly creating variables, right? An integer here, a string there, maybe a struct. But have you ever really stopped to think about where those variables actually live? Probably not. It's one of those details most of us just ignore because, Go just handles it for us. But under the hood, the compiler is making this huge decision for every single value you create. It's a process called escape analysis, and you can think of it like the secret conversation happening behind the scenes. It's deciding if your data gets a quick temporary spot in a super neat, orderly place, or a more permanent home in this kind of sprawling, messy warehouse. So yeah, let's dive in and uncover the invisible logic that makes our Go programs so safe and efficient.
Okay, so here's our game plan. We're going to look at the two worlds of memory, then the one big question the compiler always asks. We'll watch a variable actually escape in some code, bust a common myth about what really matters here, and then wrap up with the core philosophy behind it all. It's going to be a clear path, I promise.
All right, let's jump right in. Section 1, Memory's Two Worlds. See, before we can even get into the compiler's decision, we have to understand its options. And really, there are only two. Every single variable you create has to be stored in one of two totally different places, the stack or the heap. And trust me, the choice between them has massive implications for how fast and efficient your program is.
I mean, just think about it for a second. You write x equals 10, and you just expect it to work. You're not telling Go where to put it. You just trust the system to figure it out. And that trust is definitely well placed. But that decision, where that little number 10 actually gets stored, is one of the most important things the Go compiler is doing for you, totally behind the scenes. So what are the choices it's making?
Okay, so here are the two personalities of memory. On the left, you've got the stack. The best way to think about this is like a perfectly organized stack of dinner plates. It's super fast to add a plate to the top or take one off, right? It's temporary storage, and the best part, it's totally self-cleaning. Then you have the heap. This is, well, it's more like a giant sprawling warehouse floor. It's where stuff goes when it needs to stick around for a while, but man, it can get messy. To keep it tidy, you need a janitor, and in our world, that's the garbage collector, which has to come in and clean up all the old junk. So bottom line, stack is for the fast and fleeting stuff, heap is for things that need to persist.
Let's dig into the stack a little more, because its efficiency is exactly why the compiler loves it so much. So, when your code calls a function, a new frame, think of it as that fresh dinner plate gets placed right on top. All of that function's local variables, they live right there on that top plate. The computer always knows exactly where to look. And here's the magic. As soon as the function is done, that entire plate is just popped right off the stack. Gone. The cleanup is basically free. There's no need to go hunting for garbage. That space is immediately ready for the next function. It's just a beautiful, simple, and incredibly fast system.
Okay, so you're probably thinking, if the stack is so great, so fast, so efficient, why don't we just put everything there? Why do we even need that messy heap warehouse at all? Well, that's a great question, and it leads us right to the compiler's big dilemma and the really clever process it uses to solve it, which is called escape analysis.
So what is it? Well, escape analysis is just a fancy name for the process the Go compiler uses to decide where a variable should live. It has to figure out if it can put it on that super fast temporary stack, or if that variable needs to, well, escape to the more permanent and more costly heap.
And really, it all boils down to one simple but super powerful question. For every single variable you create, the compiler's asking itself this: will this value still be needed after this function finishes? That's it. If the answer is no, then great, it's safe for the stack. But if the answer is yes, well, putting it on the stack would be a disaster. Why? Because that whole stack frame gets wiped out when the function returns. So that value has to escape to survive.
All right, theory is great and all, but let's make this real. Let's actually see the compiler's decision-making in action. We're going to look at two tiny functions that are almost identical. I mean, literally, just a single character is different. And yet, the compiler makes a completely different choice for each one. This is where you can really see the logic of escape analysis click into place.
Okay, here's our first example. We have a simple function f. It creates a variable x, gives it the value 10, and then it just returns the value 10. Super straightforward. The variable x itself is only ever used inside this one function. So the compiler looks at this, and its logic is pretty simple. It thinks, okay, this variable x is born inside this function, and its entire life happens right here. When the function returns the value, nobody outside needs the original variable x anymore. So the compiler's conclusion? X can die when the function ends. It's totally safe to put on the stack. But now, look at this. The only change, the only one,
is that we're now returning a pointer to x. We're returning its memory address. We're not handing back the value 10 anymore. We're handing back a map that shows exactly where x lives. And that tiny little change, from int to *int, changes absolutely everything for the compiler.
The compiler sees this and basically hits the brakes. It thinks, whoa, wait a minute, someone outside this function is going to get the address of x. They're going to have a pointer to it, and they're going to expect x to still be there long after my function is done. If x was on the stack, its memory would get wiped clean the instant the function returned. That pointer would lead to, well, garbage, a dead end. So the compiler knows this value has to live on. It has to escape the function's lifetime. And for that reason, x absolutely must be allocated on the heap.
Now, this brings us to a really important point, a kind of mental shift we need to make. After seeing that last example, it is so easy to think, I get it. Pointers make things go to the heap, right? But that's not the whole story. It's a really common misconception, and the truth is a little more nuanced. Getting this next part is the key to really understanding the whole thing.
And here it is, the absolute key insight. Escape analysis is not about pointers. It is about lifetime. The compiler doesn't just see a pointer and freak out. It's way smarter than that. The real analysis is all about how long a value needs to exist. Pointers are just one way you can make a value's lifetime longer than its function, but they aren't the actual reason for the escape.
So, think of the compiler as a detective. It's literally following the flow of every value through your program. And it's asking, does this value or any reference to it ever leak outside the function where it was born? If it gets passed to another function that squirrels it away in a global variable, it leaks. If you return a pointer to it, it leaks. The compiler traces all these paths to see if the value is truly self-contained. If it is, it stays on the stack. But if it leaks out, it has to escape to the heap.
Okay, so we've seen what escape analysis is and how it works. But to really appreciate it, we need to understand the why. What's the fundamental principle that guides all these decisions? This brings us to the core philosophy that underpins this whole system, and it's super important.
Now, we've talked a lot about how fast the stack is, but believe it or not, performance isn't the compiler's #1 priority here. The main job of escape analysis, first and foremost, is to make sure your program is correct. It's a safety check. It's all about memory integrity. It's what prevents you from having pointers that point to dead memory, a really classic and dangerous bug in a lot of other languages. The fact that this safety-first approach also makes things faster, well, that's just a fantastic bonus.
And this really shows you how conservative the compiler is. What if it's not sure? What if it can't prove with 100% certainty that a value is safe for the stack? Maybe the code is just too complex, or it involves interfaces and the compiler doesn't know what's going on. In those cases, it will always err on the side of caution. It'll choose the heap. It would much rather have a slightly slower program that works perfectly than a faster one that might crash. For Go, correctness is simply non-negotiable.
So look, if you walk away remembering just one thing today, let it be this. This is the ultimate mental model for this whole thing. Escape analysis is just the compiler deciding one simple thing. Can this value die with the function on the stack, or does it need to live longer on the heap? That's it. That's the whole game.
So, we've pulled back the curtain on one of the Go compiler's most important and usually invisible jobs. It's a really beautiful system, all designed for safety first and efficiency second, making these tough decisions for you so you can just focus on writing your code. And it kind of makes you wonder, doesn't it? Now that you see this, what other incredible, invisible decisions is your compiler making for you every single time you hit run?